but we are starting with the layout part, which you may have already seen in the tutorials that were already shared with you, and therefore you are already working on your assignment. But it is important to take care of a few things. So that we can make good layouts in line with what we were discussing, less capacitance and all that. So let me just give you a quick hands-on run on what things you can take care of when you're making layouts. So let us say, let me make just these 4 layers for now. So in your layer map table, you have green color for active region or some other color?
Active only.
Active. So let us say this is the active for NMOS or PMOS, and this is the active for NMOS. Can we say this?
Yes, sir.
And because this is PMOS, so we will say there is a well around it. Is that okay? So now let us say we have to make the functionality of A NAND B. So what is the circuit?
2 series NMOS and 2 parallel PMOS.
Something like this. A and let us say B. Are you able to see this? Are you with me on this part?
Yes, sir.
So what we are saying is that there are 2 NMOSs and 2 PMOSs. PMOSs are in parallel, NMOSs are in series. So what would you do? You would say that, okay, let me make the polys. Arre Baba. Yeah. Let me make the polys where this poly would represent one input, this poly would represent another input. Let us call this A, let us call this B. Now let us make the contacts. Let us say this is the output, I made a contact here. This is ground, I made a contact here. This is, now you will have to tell me which one should be output and which one should be VDD.
Sir, middle one should be output.
Middle one should be output. Why?
Sir, because no, sir, because it is shared. The PMOS drain, both the drains are connected.
So वो तो मैं यहाँ पे metal से share कर सकता हूँ. See, I could short them like this.
Sir, middle one would have less capacitance. So output.
So this could be the way I could have output there.
Yes, sir. This can also be done.
Sir, actually, how you're drawing this NAND layout from this schematic that you just, I'm not able to get it.
Okay, so you're able to see these signals A and B?
Yes, sir.
The poly?
Yes, sir.
So when the poly intersects with the active in the P well, what do we get?
So one is the source and drain.
We get an NMOS, right? So we get a source and a drain there, and this is another NMOS. And by the virtue of shared diffusion region, shared active, this connection is already being built there. This connection is already being built. Am I right?
Okay.
Similarly, on the PMOS side, there are 2 PMOSs And by the virtue of this shared diffusion region, I am either making this connection or I am making this connection. Either of those two I am making. That is what my question is. Which one? Like, where would you use the shared diffusion? Like, shared diffusion should be VDD or shared diffusion should be output? That is what my question to you is.
Output.
Shared diffusion should be output. Why?
Because we get our output from the middle of the PMOS and the NMOS.
So I think it could be both because then also the source and drain, also source is also shared, then drain is also
Yeah,
shared.
they are in parallel. So
Yeah.
electrically तो कोई फर्क ही नहीं है.
Yeah, that's also what I'm thinking, sir. matlab, it doesn't make a difference to me.
It doesn't make a difference to you.
Yeah.
You already talked about capacitances, huh? See, where did I start this discussion from? From a question on capacitances. So this is a hint.
Sir,
Sir?
there can be two things, sir. One thing is in the current configuration, you are taking the metal over the poly 2 times.
Okay.
And if you do the VDD on both sides, then you have to take it to above the for the railing that would be going above for the VDD, but it would not be over the poly. It would be at a minimum DRC from the poly. Maybe you can increase that if you don't want to lose the area, so you cannot, but increase that and decrease the capacitance also.
Okay. Anything else, Devajit?
Sir, when in the middle one, in that contact to poly, there is contact to poly capacitance in both sides. So there would be initially some load capacitance also. So if we could make the parasitic capacitance less somehow, then switching could be done more faster. Means we have to discharge and charge less.
Okay. So what should we do?
So I mean, as I can see, diffusion capacitances won't change. How do we connect? Because we have this, because that is dependent, according to me, upon the active area only. So if the area is same, the diffusion capacitance, it doesn't make a difference. Like where do I'm doing the
So what
connection?
you're saying, so what you're telling me is that this area is same as some of these areas.
No, sir. So I'm saying that the diffusion capacitance depends upon what is the area of my source and drain.
Yeah. So
So
यहाँ पे, if I would connect this Y node on the outer things, this is the area that I'm looking at. है ना? Whereas if I keep my output over here, this is the area I will look at.
no, sir, but this area will come because it is source. So source area is also coming, right? Because we cannot think of only the drain area. Source and drain both come.
आउटपुट पे तो आप जो भी लगा रहे हो वही एरिया आना है ना. If my
Okay.
device, if my wire is here, why would the capacitance of this node appear on my output?
So, but the diffusion capacitance was the sum of the source, right? You said total diffusion capacitance of a.
Did I say sum of source and drain capacitance? We only looked at one capacitance. We said whether it is source or drain, this is the this is how you should calculate the capacitance. It was sum of
Okay.
two components, but what were the two components?
Okay. Right. Okay.
It was sum of two components, but what were those two components? Again, this is a hint.
That was one was the width and the LS length. So
sir, that LS part, one of the LS part gets eliminated if we do the middle one tapping. So I have
Only one
inversion
gets
layers
eliminated.
So basically दो यहाँ पर inversion layer आ जाएंगे ना sir?
Yeah. So only one LS gets eliminated, or both the LS, both the widths get eliminated? So see, even if you tell me that this area is same as this area, what happens? there is a junction, sidewall junction capacitance also, which is appearing only for this here, but in this region, it is appearing for all three sides.
Yes, sir.
Sir,
Mhm.
sir, I'm sorry, sir, but I'm really unable to. I'm like correlate this both structures, sir. I'm like, could you please explain that, sir? I'm like,
So what are you not able to correlate?
sir, there are four. I'm like two PMOS and two NMOS according to the structure. I do understand that, but
Yes.
sir, I'm like, I literally can't see those four, sir, over here.
You can't see 4? Okay.
Yes, sir.
So you see this is one transistor. Let us call this P1.
Sir, how did that become a transistor? So that was my doubt actually.
This is poly running over active region. Na?
Yes, yes, sir.
That becomes a transistor.
Okay, okay.
We saw the top level view of the transistor in the last class also. This
Yes,
is how
sir.
it looked. Nahi?
Yes, sir.
So आपने last class revise नहीं करी?
Actually, I didn't revise it, sir, to be honest.
So we did that in the last class. So that is the poly. Poly over active is a transistor. That is P1. So it has its input at A. So this is P1. The PMOS with input B is, let us say, call it P2. So this is P2.
Yes, sir.
Okay. The NMOS with input A, let us call it N1. So this is N1. And NMOS with input B, we call it N2.
Yes, sir.
Okay.
Yes, sir. Now I understand about
Now
the.
you're able to see?
Yes, sir. So, sir, a small doubt, sir. So, I'm like, even this might have been discussed, but yeah, sir. Sir, where are these drain, source, and gate regions, sir, exactly of this PMOS?
You
and-
tell me, what do you see here? Where are the source and drain regions? What is source and drain?
Source. Sir, towards the left and right, sir. I'm like of this poly.
Towards the left and right of this poly, there is a source and drain region. So आपने खुद ही तो जवाब दे दिया. सवाल क्या है फिर?
Sir, then what are these? I'm like yellow color ones, sir. Exactly. I'm like,
You're not worked on the assignment yet? You're not paint the layouts yet?
I did that, sir. But when I generated, sir, they were directly coming, sir. I'm like, I didn't see any.
Oh, so again, you should. So friends, it's important because I will be building upon what we discussed in the last class. है ना? Whatever I have discussed earlier, I will be building up upon that. So I myself try to upload the lectures within, as early as possible, within 1 hour, 2 hour of the class. Have you noticed that?
Yes, sir.
Why do I do that?
To give us time to.
Because I want you to review what we have discussed. If there are any questions, you should ask the TAs in the office hours. If there is anything else, you should discuss with us in the next class. Otherwise, I will as well upload all the lectures together and towards the, closer to the mid-sem or the end-sem exam. Should I do that?
No, sir.
The intent is that when you look at the, when you go through the class, I know you might be in one particular state of mind. You might get stuck with some idea, some previous, हम कुछ topic discuss करेंगे. There is some question pending and you are stuck there and we moved ahead in the class. And okay, later you ask the question, that questions get solved, but there is some little concept which you have missed. So I share the lectures as early as possible so that you are able to review the concepts and refresh and fill in for anything that you might have missed.
Yes, sir.
It's important, na?
Yes, sir.
So please review whatever has been if you're writing notes, review from your notes. Otherwise, I'm uploading the lectures, review from the lectures. So these yellow ones are contacts. So if you've made the layouts, you would have already seen these contacts, right?
Yes, sir.
So why this question then, Vaishnav?
I'm like, okay. So there are two pins, right, sir? I'm like, there are drain and source on the left and right of that. But I'm like, we have made contact only for one, so that we are connecting that. I'm like, we aren't mentioning the other one.
Because it's not needed.
So
Yeah. That is where I am responding to Gagandeep's query. How do we reduce the number of contacts? How do we reduce the source and drain area? See, if you would use the P cells, which I dissuaded you from using in the last class also, if you use the P cells, what will happen? Let us look at it. If you use the P cells, then you will get one transistor.
we'll get 4, sir, total.
You will get another transistor. You will make another transistor here. You will make another transistor here. And you will probably connect the poly like this. You will probably connect the poly like this again. And then you will put contacts everywhere.
Yes, sir, and make the connection accordingly.
So what happens in all this? In all this, so okay, you may say that, okay, this is ground, this is VDD, this is the shared node. I will connect them like this. I will connect them like this. Huh?
Yes, sir.
And this is again VDD, and I say this is my output.
Yes, sir.
So what is happening now? How many capacitances do we see? If we just count poly to contact capacitances, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 capacitances from poly to contact.
Yes, sir.
Additionally, there are 8 source and drain capacitances also.
Yes, sir.
So even if we say that area of shared active region even if we say that area of the shared active region is same as the area of these independent actives, what happens? Just give me a minute. Yeah. So even if we say that, this area of shared active is equal to the area of the two independent actives, what extra capacitance do I have here? I have this sidewall capacitance coming in extra, plus at least one of these drain capacitances is extra.
So, but that will be basically, but when I'm extending the shade region, then basically I don't think that will become an extra thing, because the same area would come under the shared region also, right?
So I said, if we go with the assumption, go with, be careful about what I said.
Okay.
So if we look at it over here, what would be the length of extension of this region? It would be poly to contact space plus contact width plus OD extension. So you're calling it OD, diffusion layer, you're calling it OD in your LSW? What do you call
Yes,
it in
sir.
your LSW? Yeah. So
Yes.
these 3 things will make one source or drain region. Am I right?
Right, sir.
Let us put some numbers. Let us say poly to contact is 50 nanometer. Contact width is, let us say 60 nanometer. And let us say OD extension beyond poly is 30 nanometer. So this would come out to be 140 nanometers.
Yes, sir. Okay.
Now let us come here. So in this region, we are putting one contact. So what is the spacing between these two polys? Poly to contact plus contact width plus poly to contact. Are you able to see this?
Yes, sir.
Let's put the numbers now. 50 plus 60 plus 50. कितना आया? 160 nanometer. तो effectively वहां पे कितनी थी width? 140 over here, 140 over here. The width, effective width over there was 280.
280, right.
Over here we are talking about 160.
Right. So diffusion capacitance would reduce drastically.
Diffusion capacitance reduces not just because of area getting reduced, it also reduces because the sidewall junction capacitance also does not come.
Right. Yeah. Yes, sir.
Okay. Additionally, how many poly to contact capacitances do you see now? 1, 2,
4,
3,
sir.
4, 5, 6.
6.
6,
वहां पे कितनी थी? How many were there?
8.
8. So you see, you are able to reduce that capacitance also.
So even that the capacity of the field also reduces because we have the shared drains, right? There was some field also, right? Between the gate and drain, gate and source, there were 3 components, right? So that field also, I think it reduces because of this.
Yeah, because that you can say because the drain area reduces, that can reduce. Yes, that will also reduce. The poly to drain capacitance would also reduce because the drain region is smaller in total length,
Yeah.
total area.